So in 63, we have sodium and magnesium. So it says it gives us the effective nuclear charge. So if we're looking at sodium versus magnesium, sodium's effective nuclear charge is 2.51. The effective nuclear charge is the amount of positive charge that the valence electrons actually experience an attraction to. So sodium actually has 11 positive charges in its nucleus, but the shielding of the core electrons prevents the valence electrons from feeling much of that positive attraction. So they only feel a net attraction of 2.51. Magnesium's, because magnesium has an extra proton and similar amounts of shielding, it feels a slightly greater quantity of positive charge attraction between its valence electrons and its nucleus. So you could say whatever positive charge there is in that nucleus, the valence electron feels an attraction to it of 2.51 versus the valence electron for the magnesium feeling an attraction of 3.31, a greater quantity of attraction pulling it in. So then it says use this information to compare the attractive force between the nucleus in each atom and the valence electron that would be removed by the first ionization energy. Okay, well, we kind of just did that. So we could also look at, it says to look at the table 4.6 or figure 4.6 to see the sizes of the atoms. We would expect, since magnesium has a greater quantity of charge, it would be a smaller atom, and it is. So the sodium size is 186, and I'm assuming that's in picometers. (186) versus the magnesium's relative size at 160. So really, I don't need both the size data and the effective nuclear charge data. Either of those pieces of data should be enough for me to estimate which has a higher ionization energy, first ionization energy. But those are not the only factors that we talked about affecting ionization energy. What are the other factors? Well, one is whether or not the element makes a noble gas configuration, which was part of what we talked about when we talked about 4.57. And that's the biggest factor, the noble gas configuration. But we also said that isn't always going to be able to help us. It only is useful to look at that if the element has an exact noble gas configuration already, or if it will make an exact noble gas configuration when we adjust the number of electrons by the number we're going to adjust it by. In this particular question, it says first ionization energy. So we're talking about removing just one. So we have to look at that, see if it's a factor here, and it is, because if I remove just one electron from magnesium, it will not make a noble gas, nor does it already have a noble gas. If I remove just one electron from sodium, that makes the same number of electrons as noble gas. That makes a noble gas configuration. So that factor is the primary factor, and that tells me that sodium should have a much lower ionization energy than magnesium, first ionization energy. And it does. This data also suggests the same thing, because magnesium has a greater quantity of charge attracting its electrons in, and it's a smaller atom, the electrons are closer. That also suggests it should take more energy to overcome that attraction and knock the electron out. So in this case, if this were an exam question, I would probably say something like, give 2 reasons or 3 reasons why. Well, I might say, predict which of these atoms has a higher first ionization energy and give 2 or 3 reasons why. So you could talk about the noble gas configuration is the difference between them, And you can talk about the size and the effective nuclear charge, attracting electrons. The valence electrons of magnesium are attracted closer than the valence electrons of sodium are. So it takes more energy to knock the magnesium's electron out. It has a higher ionization energy.